When I finished the lecture for this module, I was left with a feeling of, well, what should I do with this information? So I hope to be able to show you all of the pieces that you should be able to put together when performing these curved arrow electron movement questions. So I'm going to step through the first one very slowly, and then we'll move quicker through the rest. So first, the hybridization. This carbonyl carbon as well as this oxygen are sp2 hybridized. And I know that because there is a pi bond showing, and that pi bond is made up of a p orbital. Remember, carbon comes in, oxygen as well, with an s and 3 p orbitals. 1 p orbital is occupied, therefore what's left hybridizes. And that's how we get sp2. Now in our first product here, this carbon is still sp2 hybridized, as is this oxygen. But as soon as we move over to the next product, the final product, both of these atoms are sp3 hybridized. And I can see that because that pi bond was broken. When that pi bond is broken, then the p orbital is released in order to hybridize and create those that tetrahedral shape, that geometric shape around that atom. Now, I also need you to be able to see the electronegativity, the polarity involved. And I need you to see from the reactant to the product where the electrophile and the nucleophile are. Now, in number 1, we have a hydrogen transfer. This is a hydrogen transfer reaction, therefore this is an acid-base reaction. And in this case, the oxygen is acting as the base. It's taking the hydrogen away. And it's taking the hydrogen away from that bromine. And when it does that, it is making a bromide ion. Now remember, every time you do curved arrows, you need to point that arrow at an atom because it's showing where the electrons are going. So it's either at an atom or it's at a bond. Your arrow starts where there's a lone pair of electrons. And these two arrows here show the making of a new oxygen-hydrogen bond. So I've made this bond, and the breaking of a hydrogen-bromine bond, and that makes the bromide ion. So now I need to take my first product and make my second product. Again, analyzing for the bonds that are broken and the bonds that are made. Here I have the reduction of this charge, and I have added this water molecule. So in order to do that, I need to locate where is the electrophile and the nucleophile that's occurring here, because the making of a new bond like this, when I'm not transferring just a hydrogen, that's a nucleophile reaction and not an acid-base reaction. So the oxygen here of water is what is making a new bond with this carbonyl carbon. So this carbonyl carbon is now acting as the electrophile. Again, this is another point I need you to be able to pick out when doing these electron movement reactions. You need to be able to find the electrophile and you need to be able to find the nucleophile. Once this oxygen attacks this carbonyl carbon, then this pi bond is broken and those electrons land on the oxygen in order to satiate that charge, because oxygen is not going to be stable with a positive charge. Oxygen has a relatively high electronegativity, therefore it doesn't like to have a positive charge. So there you've picked out the electrophile, the nucleophile. You've noted an acid-base reaction due to the transfer of a hydrogen, as well as noting the hybridization. So you see how all of those things pull together with this one example. Now in number 2 shows sodium iodide. In organic chemistry, 99% of the time when you see a metal, that metal is delivering an anion. So when you see sodium iodide, think of this as iodide. Okay, that's really what we're looking at here. From the reactant to the product, we are trading basically. We're moving our bromine out and we're putting an iodine in. That means we have a substitution reaction, and the iodine is acting as a nucleophile and it's coming towards this carbon, which is acting as an electrophile, and then releasing the bromine as a bromide ion. The sodium is there to just balance the charges, to be a counter ion. So you see, this carbon is electrophilic, and it is electrophilic because of this polar bond. The electronegativity there is what causes that carbon to be electrophilic. So we have shown an arrow for a new bond being made. That's the carbon-iodine bond. And we've shown an arrow for the bond being broken, the carbon-bromine bond. In number 3, what we have is another acid-base reaction. This time we are removing an acidic hydrogen. See how my bromine is attached here to this carbon? Well, by inductive effects then, it makes the hydrogens on this carbon more acidic. And because of that, then this oxygen can come and take this hydrogen away, which pushes the electrons down into a new pi bond. And remember, carbon's octet will not be violated, so that means these electrons will drop onto bromine. Now we can use hydroxide as a nucleophile or as a base, and we will get into when each is when to use which in a later module. Right now, I need you to see what's happening in these mechanism steps and be able to draw where the electrons are going. For number 4, we have this carbon here, which is part of a polar covalent bond. So it is going to act as the electrophile. And in this case, we're going to make a cation, a carbocation. Some of our substitution steps and our elimination steps, for that matter, will involve the creation of a carbocation. And when it does that, then we have this water acting as a nucleophile, coming towards that electrophilic carbon, that carbon that now has a charge. And then we need to remove a hydrogen from the protonated alcohol now. So we have an arrow for every bond being made and an arrow for every bond being broken in order to show the substitution of this bromine for an alcohol group. Number 5, here we have a water molecule again. We are creating that carbocation just as before, but this time water is going to act as a base, and it is going to remove that hydrogen, which is going to create a new double bond. Again, in a later module, we will get into when water will act as a nucleophile and when it will act as a base. For now, I just need you to pick out the steps. Be able to find that electrophilic carbon and see what's going to be the nucleophile or the base. Here we're going to protonate an alcohol. So this alcohol group in an acidic environment will get protonated by coming up and after that hydrogen. And that creates the protonated alcohol species. In number 2, first thing we're going to do is make this water leave, or actually that's the only thing we're going to do. And that creates this carbocation. See how water makes a really good leaving group because it's stable once it leaves. In number 3, we have that carbocation created. And here we're going to use water again as a base, remove that hydrogen, and create the new pi bond. For number 4, we're going to make a new carbocation. And to do that, I need to remove that bromide ion. Number 5, now we're going to attack the electrophile with our nucleophile. Here's my OH. Attacking that electrophile, make sure to point directly at the atom, and that releases the bromide. Number 6, DBr. This is a deuterated bromine. Deuterium is heavy hydrogen. So here we have a pi bond, and that pi bond is going to act as a nucleophile. It acts as a nucleophile and comes after that D. Well, how do you know that if I didn't tell you? Look from reactant to product. Notice how the pi bond is now missing, And there is a new bond between the sp2, formerly sp2 hybridized carbon, and the D, whatever that D is. See, this was the formerly sp2 hybridized carbon. We have a new bond here, and we broke a pi bond. So that tells me that this pi bond is going to act as the nucleophile in this case. Now, we also need to break the bond between the D and the Br in order to create that bromide. For number 7, so what we're doing with number 7 is we're taking the product of number 6 and we're going to react it again with the bromide in solution. And the bromine, the lone pair on the bromine, is going to come up after that carbocation, which is a great electrophile, and we're going to make a new bond. Number 8. Number 8, we have this aldehyde, and we have this carbonyl carbon and the carbonyl oxygen. Now, from reactant to product, not sure how this is going to go. From reactant to product, though, we're going to add this negatively charged methyl group to the carbonyl carbon. So I need a bond or an arrow pointing directly at that carbonyl carbon. And that pushes the pi electrons onto the oxygen, which is now going to hold that negative charge. Then we'll add some acid to it. When we add some acid to it, the negative charge of the oxygen is drawn towards that hydrogen in an acid-base situation because transfer of a proton is an acid-base reaction, and we're going to create that alcohol group. Number 9, this is called an epoxide, and we're going to deal with epoxides in Module 6. But what you need to do is be able to pick out reactant to product, what is happening. So this methyl group is here, and this carbon is here. So which way is this methoxide? This is called methoxide. Where is this methoxide going to attack? Well, since it adds here, then that means the methoxide is coming towards this carbon. It's also less sterically hindered over here. And that pushes these electrons onto the oxygen. I'm going to erase these bits here. And that is all that is happening with number 9. It looks more complicated than it is. But this carbon ends up electrophilic and not sterically hindered. This carbon would also be electrophilic, but because it has this methyl group on it, it ends up sterically hindered. That methoxide is going to have a hard time getting in, which is why the methoxide will open the ring from this side. Number 10, again, we have a pi bond acting as a nucleophile, and it's going to come towards that bromine, which is going to release the electrons onto the chlorine. And the way that I know it's going after the bromine is in the first product step here, we have a new bond between that carbon and that bromine. Now we formed a carbocation, and the chlorine can then attack that carbocation. And that's how we form the product. Finally, number 11, now we have another acid-base reaction, and I can see we have an acid-base reaction because we have created a new pi bond. And in order to do that, we need to remove a hydrogen. But where does that hydrogen go? The N or the F? Well, it's going to go onto the N because that's what's shown in my product. So the N comes after the H, and also the ETH. This is an abbreviation for ethyl. I can't spell it. Ethyl, E-T-H-Y-L. So this is N and then CH2, CH3. Like this. So it's this lone pair of electrons that is acting basic. It's taking the hydrogen away. And when it takes the hydrogen away, those electrons drop in to make a new pi bond. When that new pi bond occurs, then the bromide is released. So that is how we show the reaction steps while utilizing our knowledge of electrophiles, nucleophiles, acidic hydrogens. Acidic hydrogen is always going to be on the carbon adjacent to the carbon that holds your your halide, couldn't think of the word. We also note the hybridization with this. So that's how we can take a lot of topics from this module and combine them into one.